So, hello everyone. It's my pleasure to welcome you all to our presentation about Dufour Aerospace. First of all, I'm going to give you a little introduction because I see that a lot of our guests are not members actually, or I have never seen them. And we first of all want to give you a little introduction about our association and what we do. And maybe someone will join after this presentation. So, what is our idea? We were founded initially as an academic initiative to actually unite all kinds of students that are interested in aviation, in any kind of aviation. That was almost 10 years ago, so our 10-year anniversary is coming up. As of today, I've looked it up, we are 187 members, so a rather average academic association. And as I mentioned, we have all kinds of aviation interested students. For example, model flight, gliders, helicopter, motor flight, also flight simmers or spotters. Any kind of aviation interest is fine with us. We are open to any student that is from one of Zurich's universities, so ETH, ZHW, also Winterthur counts, and the University of Zurich. Also, if you're not a member of one of these universities, you can join us as a partner. Yeah. Our goal is mainly to bring people together, so the exchange, also in an academic context in aviation, to also bring aviation to the people, and have good friendships and go together to events and support them. So now, especially what are we doing? We do scientific presentations like today with Dufour, or also in the past. We go to see guided tours at aviation-related places. We visit air shows. Once a month we have our drink-in where we meet together and talk about aviation and all kinds of topics. Once a year we try to do our fly-in, where from all parts of Switzerland members who are pilots can come together to one place and we meet. And members who are not pilots can actually ride along, and that is a very nice opportunity for people who don't have access maybe to join. Also, sometimes we do fun events that are non-aviation related, just for the friendships. And also, we organize opportunities to fly with one of our members if someone is interested. Some impressions of what we have done in the past, maybe, so you get a better overview. Just this month or last month, we went to Pilatus Aircraft. We had a guided tour at their factory that was very interesting. To finish off last year, we had a fondue event, which was very nice. We also had the opportunity to get a tour at the Rega headquarters in Kloten, where we saw the heli and jet maintenance and the operation center. That was very interesting. This is actually an impression from our last fly-in, where we met up in the Jura in Brössecourt. And as I mentioned, a lot of people came from all the parts of Switzerland, and actually we managed to fill up the entire apron almost with aircraft from us. So all these aircraft are just from our association, or from pilots of our association. So that was quite nice to see. Also, we got a very nice tour at the Skyguide headquarters. We could visit their simulators and also the aero controls. And in last summer, we had also an event together with the student initiative, or the Fokusprojekt Isling, from the mechanical engineering department, and they gave us exclusive insights into their research for this sustainable aviation sling they modified to work with an electric motor. And also, on a more technical aspect, we went to visit the maintenance at SR Technics with Helvetic, and they showed off their new Embraer E195 /2, which is the new variant. And lastly, also we do introduction days, in this case with paragliding, which was organized by our members who are paragliders and allowed all our members that maybe have no contact at all with paragliding to get an insight or access to this domain of aviation, which is this, of course, would not work without our sponsors, so we're very happy to have Skyguide with us on board. They also facilitated the visit to the simulator and the air control. The Horizon Flight Academy also sponsors us, and the Cockpit, which is a magazine, an aviation-related magazine. Who are we connected with? Actually, at all three universities I mentioned, we are associations that are recognized, so we have all the benefits. We have also a lot of members of the Swiss Association of Aeronautical Sciences here today, so we want to mention them as well. And we exchange events. As you see, they come to our events, we can go to theirs, so that's a very nice exchange. Also, we have the Swiss aviation journalists where we can exchange a lot, and also with the Center for Aviation Competence. And we have our counterpart at St. Gallen, the Aviation Club of St. Gallen, and also the Academic Flight Group of Zurich. They have gliders and fly with the members on their gliders. What are we doing this semester? So the semester is already almost, it is at half point. So what are we doing? Tomorrow, in Winterthur, we have our drink-in. So we meet up in the boiler room near the train station. So if you have time, of course, you're very welcome to join and meet some members there. On the 21st of April, on a Friday, we will visit the Aero Friedrichshafen as a group, just as last year. And it is actually the leading show for general aviation, where they show off new technology. And this was our small group last year. Then, very interesting, we still have open spots also for this. We have organized an introduction day to gliders, so people who have never experienced gliding, flying without an engine, which is very fascinating. We can only recommend that. We have a winch and also glider tow, and we have our own flight instructor, which will accompany this day. So we're very happy to announce that. We will visit an air show near the Hohenkasten in the same week on Friday. And finally, we have our General Assembly on the 8th and 9th of July, which is again combined with a fly-in as last year, as you can see. As I mentioned, during all the year, we have this jump seat, or we call it jump seat. We have a WhatsApp group where pilots who have empty spots can write, and then members who opted into this, let's call it service, or to this group, they can join in, and we do this on a private basis, just with cost participation. So if you have any questions, you can see at our website, aviatikverein.ch, and it's really easy on Facebook and Instagram. It's just Aviatikverein, or you can write the mail to info@aviatikverein. Also, a lot of board members, including me, are here today, so you can also come here and ask us any questions. If there are none so far, I would like to hand over to Timon, yes, our speaker from Dufour Aerospace.
So I hope I can hold up to the scientific presentation requirement. It's maybe not as scientific as others might be. My goal today is to show you what Dufour Aerospace does. We do a lot of different things. There's a lot of different technical areas. I will touch them all a bit on top, but I'm very happy to also go into a bit more detail if you have questions. So please also during the presentation feel free to raise your hand and we can make it a bit more interactive. About me, I'm Timon, as you heard, Timon Wehmann. I studied mechanical engineering here at ETH, and a couple of years ago I joined Dufour Aerospace as an intern. We were still a really small company, about 6 or 7 people, and we saw it grow over the years, and now we're about 45 to 50 people over 3 different locations here in Switzerland. It started all in Visp, in Wallis. Then we had an engineering headquarters in Altstetten. And now, since a bit more than a year, we're operating also in Dübendorf. We have a hangar there, and we can do flight testing, which is really amazing. It's a really unique opportunity to be in Dübendorf on the military airfield and do almost daily flight tests. But yes, you will see some pictures from this afterwards. So I titled the presentation, Dufour Aerospace, Reviving the Tiltwing Concept. And I don't know how many of you are familiar with what the tiltwing is. It's relatively explicit, relatively straightforward. It's a tilting wing. And it's actually a concept that was, or that is existing since many decades. You might be aware, eVTOL is a trend word nowadays. It stands for electric, that's the small e, and VTOL, vertical takeoff and landing aircraft. So it's these kind of air taxis, drones, whatever, where you can basically land on top of a skyscraper or on a house. You can transport rich people to the aircraft and back, and there's all these many concepts and all these many companies also working on such things. So are we. But what we do, we basically just copy-paste of what already existed in the past. That is not an eVTOL, but a VTOL. It's not electric. It's with conventional turbines. It's the CL-84 from Canadair. It was developed during the 50s and 60s, and it's a tiltwing aircraft. So a tiltwing aircraft, that means it has a wing that can tilt. It can hover and take off vertically, and then once it's in the air, it will bring forward its wing, transition to airborne flight, and then fly like a conventional aircraft, pretty much. You can see, in order for it to actually hover and have pitch control, there's a little fan or a propeller, I must say, in the back, and they have 2 main rotors in the front. And therefore, with the propeller, they get the pitch control. With differential thrust on the main props, they get the roll control. And then with the flaperons in hover, you get yaw control. So that's the basic fundamentals of how a tiltwing aircraft works. Funny enough, they were not the only ones doing this, the Canadians. There was even the US developing tilt wings. This one is the XC-142. It's a 17-ton aircraft. It was flown by many, as well as the CL-84. Actually, it was flown by many test pilots. Each aircraft, more than 20 different test pilots. There's hundreds of hours of test data, lots of documentation. And you have to imagine, back in these days, there wasn't a whole lot of like digital control systems and fancy stabilization and whatever. It was pretty much mechanical. There were gearboxes doing the control allocation. If I read these reports, I'm like, these people back then, they were really smart. What we do nowadays is just take a microprocessor and implement the laws on there, but they actually had to think how to properly implement this mechanically. So it's quite impressive to see how that actually worked. I said this is a 17-ton aircraft, and that kind of proves one of the points why we derive from these examples. You cannot artificially, or you cannot just scale any concept, right, to any size and any dimension, because your Reynolds numbers, they obviously change. And what might look really cool and easy to do on a small drone, 10 kilograms, might turn out not to be as easy on something that big. We believe that especially the lift and push concepts and similar concepts, they have challenges, just because it doesn't scale as well as you would probably think. However, this is a really big aircraft, and it flew quite well. What I show you now is footage from the CL-84. So that's the one we saw first. This is recorded in the 60s. You can see it hovering, doing some maneuvering in hover, and then we will see a nice forward level transition into cruise. And it just really demonstrates the agility of these aircraft. And back then, obviously, Vietnam War was going on. There was an incentive to kind of build the next good aircraft. They equipped it also, obviously, with machine guns and different weapons. Later in the video, we would also see how they tried to shoot that stuff and so on. And overall, really a nice concept. So you might ask yourself, why did this not make it? Why did no one build it in the end? And funny enough, it was pretty much just benched due to political reasons. That was one thing, because Vietnam War was coming to an end and no one wanted to spend hundreds of millions more to develop new aircraft concepts. And also, they had technical challenges and difficulties, and it's probably not so hard to guess, mostly just the mechanics on like how to run all these rotors and the linkages between the control actuators and the whole scheduling and all this kind of stuff. Especially in the CL-84, they had to have, so they had 2 turbines in each wing, and they had to have a mechanical link between the two in order, like if they have an engine loss, to be able to recover the aircraft and so on. So this was a massively complicated design, even though it looks quite simple actually from how you see it now. I think now it's about to do the transition. Yes, you can see the wing comes forward quite quickly, and the aircraft accelerates in a matter of seconds actually to pretty much cruise speed. And in this case, it's a stable aircraft configuration. And that's also one of the factors we leverage, or we want to leverage for certification, that in conventional flight, we're like a normal aircraft. We don't need an active control system like with super tight control loops stabilizing the aircraft, because it's pretty much stable by itself. So this video takes you another 10 or 15 minutes. I'm not going to show the rest of it, but obviously if you search it on YouTube, you will find it. CL-84, that's how it's called. The question now is, what do we do if we say we revive the tilt wing concept? We believe that today, or in the times we live in, we have new technical opportunities to basically take such a concept and make it easier and cheaper and more effective. So that's the 3 fundamental things. It's relatively straightforward. Electric propulsion instead of complex combustion engines or turbines. That means a lot less moving parts. You see that in the car industry. It's super cheap and easy to maintain. Also, you get quite a power density on these motors. So that gives you also the advantage that you can like distribute your propulsion way more. So you get way more redundancy. If you have a big turbine engine and you want to split it in 10 smaller turbine engines, it's a nightmare in many different aspects, including weight. With electric motors, this is possible with not too much of a kind of a downside. The other one, and that's one of the aspects where we kind of do it a bit differently than most other eVTOL companies, I would say. We choose a hybrid approach. That means we don't go full electric. Of course, this is from a kind of greenwashing perspective. It's maybe not as easy to sell, but it's what actually works, I would say. Because with pure electric, you don't get the range that most people would look for. And we combine electric motors with batteries for the parts of the flight where we need a lot of power. And then in cruise, where we actually just need a fraction of the power you need in hover, we have a generator system which is just sized big enough to like maintain the cruise and be able to recharge the batteries. And then you come in for a landing with an empty tank but full batteries, and no drop of sweat. You can just land. You can do 2 go-arounds. But the batteries, they are just sized to a minimum to really just account for a landing and a couple go-arounds. And that means, because as you know, batteries to this date, they're still about 20 times less energy dense than fuel. if you account for all the packaging and so on. Of course, there's lab cells. They might show way better data, but until you have it finally in the aircraft, it's heavy. And this also gives us the advantage that once a super nice cell appears, or once we have a fuel cell or whatever else, we can just take out the generator and we stick the new thing in, and it still works. So we believe that this is the right way forward to actually have something that works in operation that we can sell. And the third one is obvious. Today we have good availability or the availability not so much in these times, but we have CPUs and microprocessors. They're quite cheap and quite straightforward to work with. And so we go for a fly-by-wire control system. It's, of course, a bit of a challenge from the certification perspective, because that's so far what airliners pretty much did, or fighter jets. But there's ways to do that, obviously, and we are building our in-house flight control system currently. So what is it that we're building? It's a tilt-wing aircraft with a new look, with distributed electric propulsion, with a hybrid generator system, and a hybrid electric aircraft that eventually will replace helicopters. That's what we believe. One of our co-founders, he's a Air Zermatt pilot since 30 years, so he knows the helicopter business perfectly well, and he's like, that's the thing that we need. Maybe not so much for Air Zermatt per se, because they often fly into deep mountain valleys in very bad weather, kind of hovering for long times, trying to rescue people from crevices or whatever. But that's only a fraction of where helicopters are used, sling loading and so on. But most helicopters are used is just transport from A to B. And so if we build a system like this, if we build an aircraft like this, that can operate at a way lower cost and is more efficient than helicopters, and it can use the exact same infrastructures as helicopters do today, there's a huge market to sell these into as of right now. So we don't depend on new infrastructure or new concepts or new regulations in how you have to have these skyports in the cities and whatever. It's something we can use as of today. One of the nice aspects of the tilt-wing configuration as well is that we can fly in every configuration. So even if our wing gets stuck at 45 degrees or something, the aircraft is perfectly well controllable, and we can just fly it. So it's not that you are in hover and then you need to commit and you hope that you get out in cruise, and vice versa. No, it's really a continuous flight regime you can basically use. That's also what I mean here with the wide transition corridor. The transition corridor is a plot. I don't have it here, but it's basically where you are in your transition versus what your airspeed is. And these tilt wings, they allow for a certain wing tilt angle quite a big range of different airspeeds you can be at without stalling the wing and falling out of the sky, because you have a blown wing in all parts of your envelope. You see the motors are nicely distributed over the wing, and therefore from hover to cruise, you have a nice airflow, which keeps your flow attached more or less, and you have full control with your aerodynamic surfaces. You might wonder, does that always work? Is that always the case? There is one, or a couple more as well, but there's one worth mentioning, constraint. If you find yourself doing a back transition and sinking too fast, you will start having upward flow over your wing, and your aerodynamic surfaces, which are here, they start to become less effective. We had this happen a couple times on some of our prototypes when we started sinking too much, and then we started losing yaw authority. So that's one of the things you have to be careful. But if you look how a helicopter approaches and what sink rates he has, it's kind of similar to what we actually can do. Yes, so that's what we're doing. I will show you a quick 1 or 2 minute video and comment a bit on what's going on, so you see the actual things flying. And then I will go into a bit more detail down the road. So this is our first prototype. This flew 3 years ago. Oh, it's a bit loud, huh? This one is Aero 1. It's an electrified aerobatic aircraft, also about 3 years old. Initially sponsored by Hamilton, and then we rebuilt the whole propulsion train. So second generation, which is flying now. This is the second generation of the VTOL concept from Aero 2. I'll explain it in a bit more detail afterwards. And you see here we have a cargo bay where we load in the cargo and off it goes. This one is a prototype. It doesn't have the full cargo or payload specifics that we obviously want to sell later on. So it's flying empty right now. But what we're targeting in the long run is a 40 kilogram payload over 400 kilometers of range. And this one that you see, it's our small scale test platform. It's Aero Mini, fully 3D printed. We'll also show you in a bit more detail afterwards. And then this, obviously, a render of what you can imagine Aero 3 to look like, and also how it can operate. We have plans to build a prototype, like detailed plans. It's just a matter of actually having the time, the team, and the budget to build the full-scale prototype, because as you can imagine, building such a big aircraft is expensive. So what we actually decided to do is to start small with this one. That's Aero 2. You saw in the video in the beginning, you saw this aircraft doing the full transition, hovering, then transitioning forward. I said it's like 90 kilograms of weight. It has a 4-meter wingspan, and it's really just a tech demonstrator. It was thought to be a 1:3 subscale, roughly, of the real thing, because back then the main idea was to go for Aero 3. However, this tech demonstrator worked so well and was really impressive also to our investors that many of them were asking, why don't you start with this one? Why don't you sell it first and you do the Aero 3 a bit later on? So the Aero 3 is the big one, the Aero 2 is this one. And that's when we decided, yeah, that actually makes sense, because it will also help us to learn a lot more, a lot faster, and with a lot less budget. It still needs a lot of budget, not to say it's cheap, but it's orders of magnitude faster and simpler to do the development on this one. We are currently in the 3rd generation of our prototypes and building the 4th, which is the pre-production of what you see here. That's a rendering still. And we intend to start selling these drones in 2025. We have customers already ordering many dozens of them. And the first 40 we will deliver in mid-2025. And so the rough specs of it, 40 kilograms of payload, over 400 kilometers of range, wingspan of 6 meters, and an overall aircraft weight of 210 kilograms. Again, it's a hybrid approach. So we have here on top, we have a hybrid system. So it's a really weight-efficient bike motor from Suter Industries. It's a Swiss company. They do racing bikes with a generator. Then down here, we have the loading bay for the cargo, which I think we see here, yes. And basically, yeah, the contrast is a bit bad, sorry. But basically, the operator just approaches the aircraft from the front, can open the hatch, take out his payload, put in another one, close it, press the button, and off it goes. So obviously, there is no pilot on board, so we automate the operation. And this in itself is a challenge, as you can imagine. How do you make it safe and not risk killing people with it? That's what the authorities are really concerned with in the end, understandably. And so where we start to operate, we basically don't have any people. So we start with our entry into service product, we start in sparsely populated areas. That leaves us at a SAIL 4 from a certification perspective, which is still quite some work to achieve it, but it's way, way simpler than having an air taxi flying in a city or something. It's orders of magnitudes. And so our initial applications will be in the US and in Australia, flying just remote locations, mainly for medical goods, potentially organ transport, blood samples, blood in general to keep people alive, whatever you can think of. The good thing with medical goods is that it's quite valuable, it's time critical, and it's relatively small in size. So drones are perfect for it. And you might also know that in Africa today, they have already dozens of drone companies operating with smaller payloads, like 2 kilograms to about 5 or 6 kilograms, with the same type of cargo. That's last mile delivery that they do, and what we do is middle mile delivery. So we go from hub to hub or from hospital to hospital, while as the other ones, they go potentially more out to the field, to the direct customer. Also Zipline, for example, you might know, they started a partnership with Walmart last year. So they, as of today, they drop parcels in people's backyards, which is super crazy and cool. But that's not something we would do. We would focus more on the hub-to-hub middle mile logistics. This is just to give you a bit context of the size. I keep referring to it as a drone. It is a drone, but it's also an aircraft. As I said, 6 meters, quite heavy. You don't want to be too close when it starts. So yeah, it's a new type of aircraft, I would say. And here's a quick comparison. That's the 2nd generation prototype next to the helicopter from Thomas, our CEO, the Air Zermatt pilot. Yeah, it's really an aerospace thing. And yeah, not just a drone. One more render to focus a bit on the aircraft configuration. You can see on this one we have 4 motors and 8 flaperons in total. So this aircraft is massively over-actuated. We have way too many flaps than we would actually need, but this gives us an advantage that we can tolerate more faults in the system, and they don't end up being catastrophic for the operation, or not even hazardous in most cases. That means we have per nacelle, so per gondola where a motor is, we have 2 completely isolated propulsion streams. That means 2 batteries, 2 motor drives, 2 chargers, and a double wound motor. So the motor is physically 1 unit, but from a system perspective, we treat it as 2 motors with 2 separate windings, and we drive them from 2 separate motor controllers. So basically in one wing, you have 1 motor, 2 motors, 3 motors, 4 motors, and then up over here, is 8 virtual motors, 8 flaperons, and then again here on the tail, 1 double wound motor with 2 redundant propulsion streams. So this aircraft is redundant in order to ensure safe operations, but also to keep it flying even if it would have a failure on one of the actuators, for example. And then the only thing you have to do once you land is to, if a servo is faulty or something, is to swap the servo and off you go again. And it's not like with a helicopter where you have the famous Jesus nut on top of the rotor head, where if this one thing lets go, you're down and in the grave pretty much. On this aircraft, there's no single point of failure. So let's go to Dübendorf. That's where our hangar is. It's in Halle, I always confuse it, Halle 7, I think. So it's down at the Air Force Center, close to where the Rega basis is located. And it's super nice. Since we're able to fly out of there and have our prototypes there, we're getting way more efficient because you can do flight tests way easier. Before we were flying in Raron, close to Visp, and because most of the people were based in Zurich back then already, we had to travel long distances, and of course you always forget something in Zurich and you have to kind of get it. And even now, as we have our not our headquarters, but our engineering office in Altstetten, and this one is in Dübendorf, just across the city, it's already a nightmare because stuff is always in the wrong place. But 2 years ago, it was even worse when most of the things were in Visp and so on. So this is a massive improvement already. And we're looking to transfer more and more of our operations to Dübendorf. We have great connections also with the military and the innovation park, so that's really helpful. What you can see here is on the left side, X 2.1, X for experimental, 2 for Aero 2, and 0.1 is our second prototype. 0.0 was the first one you saw in the other video, and this one is X 2.2. It's our third prototype. We're currently still working on making it ready to fly, but that's coming in the next few weeks. And yeah, that's kind of a bit of hangar life, just how it usually looks like. A lot of people working on things. Obviously, there's always issues that you have to find and debug, and sometimes it's a bit stressful. But still, I often then say or tell myself, like, what else would I want to do? It's working on an airport, in a hangar, on a cool new aircraft. So, yeah, it's worthwhile doing it. Again, this is the other one, 2.1 that you saw. This is also equipped with some nice flight test instrumentation. We have on top there, you see a long air data boom with angle of attack vanes and side slip vanes, and that really helps us to validate our models that we use for our simulation and validation of the control system. So yeah, this aircraft was pretty much flying for the last 1.5 years, gathering lots of data, again, flying full transition, and now it's about to be retired as we start flying with the new one. So how does that look like when it flies? That's one of the flights, I think, from last summer. Yeah, I'll just show you. That's 2.1. This is Whiskey 1 at Dübendorf Airport. You can see the aerospace or the Air Force Center in the back, the nice museum there, and our hangar is pretty much back here. This is now hover and really slow transition forward, and that's how we do the envelope expansion on these aircraft. We always start in hover, and we just gradually bring the wing further forward and a bit further forward and a bit further forward, and we always have a safe way to come back, basically. So usually it's 5 degrees increments, and in order to do the full transition and the full tuning of an aircraft, it takes 2 to 3 months, usually. Because you need to, obviously tune it quite well in every phase of flight, such that if you do the back transition again, you know you're in a safe regime. We have our own data systems and logging systems. This is Grafana. Some of you might know it's an open source display program. So the cool thing is, like all our aircraft, they're connected over 4G, over the internet. And in order to, for example, reflash it or to remotely access it or something, you just have to have your PC with you, and you don't have to constantly walk to the airport, to the aircraft, plug in the USB cable, all this kind of stuff. It's really hands-free if it works. It works better and better with every day. But that also means it's just every time it's operating, there's just a whole bunch of telemetry being logged, and we have all these nice tools to then evaluate and post-process, and again make our models more accurate, to then de-risk the next aircrafts we're building and kind of extrapolate from the data we gather. That's also a bit of hangar life. That's the flight test team right here. That's Daniel, our flight test lead. He came from Sikorsky a year ago. He led flight test campaigns there with some of their new X2 prototypes. So it's these, I don't know how you call that in English, but like helicopters with 2 rotor blades, basically. Quite cool stuff. And a lot of these people, they decide at some point, oh, I want to get my hands dirty again. I want to work on something new and in a small team. And therefore, we are really like blessed somehow with having lots of really talented people without doing too much of promotion or advertisement. So yeah, he's just one of a really great senior team we're having. And here they're training some of the flights in the simulator. For flight tests, you always need 3 to 4 people. So you have 1 remote pilot, as it's still not fully automated, but we're working on this. You have a telemetry engineer who's looking at the telemetry and he's calling out, for example, oh, battery is getting low or temperature is hot or one of the motors is getting into a current limit or something. And then you have the observer who's always looking at the aircraft, also filming. And in case of an issue, he would point the remote pilot to the aircraft right away. That's how we do the flight testing. We have an on-screen display and a redundant video link. And this is really helpful to have this first-person view to fly the test points accurately, because you want to, at some point, fly, let's say, with a certain pitch attitude and a certain airspeed, and you need to target all these values quite accurately. And if you just fly line of sight, that's really hard to do. So we developed also this on-screen display. It's based on a really old software, Vista 2D. Maybe some of you know it. Our propulsion lead worked with Solar Impulse in the past, and they used this software to do all the ground controls when they flew around the world. So it's really great to have all these people giving inputs from their experience and really pointing us in the right directions in what tools to use and how to build these systems up, especially for flight test. Because the flight test vehicles, they're quite a bit more complex than what we want to sell in the end. In the end, it's just pushing a button and it should do the thing. But as of today, there's so much engineering going into just getting the data, being safe, in expanding the envelope, all this kind of stuff. And so this is one of the most recent videos. Again, Dübendorf Airport. It's a 360 video. It's one of these new things you can do with GoPros. You can look around. And this is now flying down the grass runway. You can see almost full transition. We have these strands on the wing to help us understand a bit more what happens aerodynamically. Then we tilt the wing back to about 30 degrees to do a nice coordinated turn. Then we are on the main runway, lining up for our approach. These operations are all trained in the simulator. We have a one-to-one representation of the Dübendorf airfield, and Daniel and the team are, like, every time we have a new operation, they train it first in order to really be aware, okay, when I'm there I need to do this, when I'm there I need to do this. And so that's really helpful to keep our operations safe and reliable. Yeah, that's relatively smooth landing. We had some issues in the past with when the pilot actually looks at the FPV screen, it's really hard to judge the height. And sometimes we had some bumpy landings. And now we finally have a vertical speed controller, which helps us to bring it down quite smoothly. A lot of times flight test looks like this. So the aircraft is on the ground. The video before was like a 3 or 4 minute flight, but the time that goes into doing this is a lot more. So we need to coordinate with the tower, we need to coordinate with the authorities, we need to make sure the aircraft works. Always, obviously, there's a bug in the last minute, and then you have to decide, should we proceed or not? So yeah, oftentimes there's just a lot of people standing around here trying to solve an issue. And then finally, we can usually work. And yeah, you can see as a startup, you have to be a bit innovative sometimes. This is an old post Vageli that someone got from Tutti, I think, or Ricardo, and it's really practical. So it's great to work with people who kind of have this practical mindset, and just with what we have, we try to do the best and stay efficient and safe, of course. So over to our test fleet. This is Aero 1. That's the aircraft you already saw in the trailer. It's a kit aircraft. It's a sling. No, not a sling. It's a silent twister. E-sling is having a sling. And the propulsion unit, like our founders back in the day, had that as a hobby project, basically, to just electrify one of these kits. They built that within, I think, a year. And flying it, they realized how attractive electrical propulsion actually was for aircraft, because before they even realized they were up in the air. You have a lot of power density. However, after flying for half an hour, the battery gets soggy and not much power is left. So that's the downside, obviously. But seeing really how much power this had, the idea came up to even start with VTOLs. And then about a year of research went into looking what kind of concepts were around in the early days, and that's how we then found out about the tilt wing concept, and that's how it all started, really. The other test platform is Aero Mini, as I mentioned before. This one is a lot smaller than the other ones. It's 2-meter wingspan. It's about 10 kilos MTOW, and it's fully 3D printed. So all you see here is just 3D printed parts with some carbon spars. We found a new 3D printing material called lightweight PLA. Some of you might know it was a big hype in the RC model industry when it came out about like 3 or 4 years ago. It allows you to basically print parts which are a lot more lightweight than like conventional 3D printing would do. It's printing at an extra high temperature, and then it foams the plastic, so you can massively reduce the material flow. And that's super practical, of course, for rapid prototyping. Oftentimes we adapt pieces to feature new sensors, or we want to try new concepts, like Julia did in his master's thesis. He worked on this quite a lot. He looked into having another concept of the tail thruster. Here we have a propeller, as you can see, and there's a lot of different ideas how you could make that a bit more optimal. So yeah, it's our testing platform. We use it for validation of software releases. We use it to test new systems, and we try to keep it as much in line as we can with Aero 2. So all the interfaces are pretty much exactly the same. So we can run code on this, we can run it on Aero 2, we can run it on our simulation and hardware in the loop in our simulation. So we really have this kind of stepping approach to make safe and efficient development. Again, many of these Aero Minis stand around in the hangar, also in Altstetten sometimes, because a lot of people from the controls team, from embedded software, they kind of try all their stuff on there. And that's how this one flies. That's again in Dübendorf. The video is only half speed, otherwise it wouldn't look so smooth, I think. We had some fun with one of our FPV drones chasing it. Yeah, and oftentimes we are asked, is this your product? But no, this is really just a prototyping platform. You saw there's like tape around and stickers and whatever, and it's really something if it breaks, you just fix it again and it flies again, because that actually happens quite often. Sometimes they land like this, sometimes they're completely demolished, but you want that to happen on such a platform in a safe environment and not on your Aero 2, or of course not on your Aero 3. So if we develop new functionality first, obviously we use our brain, then we use a second pair of eyes to review what we did, then it goes on the simulator, then it goes on this, and then it goes on the real aircraft. And it's just the step from pure software to hardware. It's harder than you think. There's always something that doesn't work. And yeah, that's why it's good to have these. That's the simulator that I mentioned. It's an old version. The landing gear is a bit skewed, but we solved that now. Also, most of the times we actually don't use the nice visualization that you see here, and that actually is now much more nice. We now have an integration with the Microsoft Flight Simulator, so that gives you really nice visuals. But that's just for the user experience and for the remote pilot to train. What we really just need is to have our models running and updating, and we have unit checks that then run through, and we see if the aircraft is actually doing what we expect. And since we have this available, the controls team, so the guys working on flight controls, they're a lot more effective, because on a daily basis or even on an hourly basis, they just test new things, and they see right away if it works or not. Whereas before, we mainly just used Aero Minis and a gazebo simulation, an old one, which was really buggy. And it's just crazy to see how much this helps to have the right tools to stay efficient and quick in development. Then also we have test rigs. That's a so-called iron bird. So a bird that doesn't fly because it's out of iron, but it allows you to have all your systems attached there and wired up. And as always, you test your individual system, it seems to work, and then you connect it with a bunch of others, and then it doesn't work. And that's exactly the things we test on here. And it gives us good access to the things. It gives us more time to solve issues before it actually goes onto the aircraft. We still have to learn it sometimes in the hard way. We just, the other month, we had a modification on one of the big ones, and stuff didn't work. And if it's already on the aircraft, it's a pain to access it and to debug it. And so, yeah, we're really pushing for these iron birds. Then one more test rig is the hybrid propulsion test rig. I so far didn't really talk about it, but as I said in the beginning, we don't believe that pure electric is right now already something you could sell, at least in our market. For more short haul applications, obviously that's still valid, but we wouldn't reach the 400 kilometers at all, pure electric. So this is the bike motor together with the generator that is running on our test rigs today. You can see it's a bike motor with what's in the front. Yeah, you can't see it anymore, but here that's the generator with the cooling fans. The generator we also use to start the engine. So in the beginning, you use it as a motor to start the engine, and then it switches from motor to generator, and it actually produces electricity. And so what we target for our application is 15 kilowatts continuous. We need about 11 kilowatts for sustained cruise, level flight. But in order to climb, to cross a mountain range, for example, you obviously need more power. And also when you take off, you deplete your batteries to about 70, maybe 60%. And the first thing you want to do once you're in cruise is to recharge your batteries, because that's your safety net, so to say. So even if this motor stops working mid-air, it's not really an issue, because we can safely go to our alternate place and land there with just the battery power. So I think I'm about to be done. That's one of the last slides. That's our Altstetten office. Again, you can see many Aero Minis. One here, controls team is working on it. One here, embedded software. And one here that's actually retired, just hanging there. But these are our test platforms, and you will find them in all our offices. Last but not least, that all wouldn't work without a highly skilled team. We have a lot of great people that, as I said before, they're just attracted to come and work somehow without us really headhunting or anything. And for me, I said it in the beginning, I'm a more or less fresh graduate, but I get to work with all these people, and that's super, super cool, and I can learn a lot, and I learned a lot over the past years. And with that, I'm just saying we're always looking for passionate and highly skilled people to join us. It's a great endeavor. It's sometimes stressful. It's a lot of work, but it's really rewarding. So, yeah, if you're at some point looking for a job or are interested in aviation, you can find me with my email address up there. Also, on our website, there's a careers page. We had quite a hiring season just now, and now it's getting a bit more calm. But yeah, there's always opportunities. Also for potentially master thesis or bachelor thesis, as Julia did his master thesis with us, that's always quite welcome. Oftentimes we also have interns in their masters, and then they do their master thesis with us afterwards, and some of them even stick around and join the team. So yes, our relationship with ETH and in general the Swiss universities is really good, and it's great to be here because the Swiss environment I think is really helpful. Even to be able to test in Dübendorf and all this kind of stuff, I think it's quite unique. It's really a blessing. That's it. Thanks a lot, and we can do questions afterwards, I think. Okay, so the question was about manufacture of e-motors. I have to repeat it so the recording knows about it. We have different ones. On all our prototypes, we use different brands. As of right now, we have on the latest one, we have Plettenberg. It's a German motor manufacturer, also on the generator, actually, of the hybrid system.
And the second question is, have you ever thought about how to integrate those remotely piloted drones in a high-traffic environment? Not in Africa, in the bush, but let's say more in an environment like urban cities, where you have remotely piloted drones of the size of 200 kilos running around.
Yeah, it's definitely not easy. So the question was about integration in airspace and more populated airspace. We, on purpose, try to avoid it with the first product. But obviously, you can use transponders, also anti-collision systems. We have some good contacts there where we do proof of concepts about this. And then often obviously it's also the question, is it cooperative airspace or uncooperative traffic that you have? If you have your paragliders there, it's going to be super hard. If they all have a transponder and the TCAS, it's a bit more straightforward. But also, especially as of today, with the people and the companies we see operating, they just really have to agree with their authorities on some corridors they operate, and then it just becomes a matter of flying the same corridor all the time, like an airway, basically. But that's going to be one of the challenges. But luckily, not only us have to work on this, and there's going to be nice off-the-shelf solutions in a couple of years that we can integrate with. Julia?
I wanted to ask, what have you planned for the mission planning, basically? What is the operator going to interact with? Is it going to be just automated platform, fixed path? I mean, is there something in development there already?
Yes, there is. One of the challenges is what standards do you kind of adhere to? Again, sorry, question was about mission planning and how that all works. We try to stay as agnostic as we can. So as of right now, it's just simple waypoints. On top of that, we might, with our own custom solution, do a bit more optimized path planning and path following. But creation of waypoints and sending waypoints and updating waypoints, that's really straightforward, and most systems will be able to work with it. Because one of the things like our customers tell us, and they also use other drones, of course, for each drone, they need to have another ground station. And oftentimes the ground station is even bound to the specific drone. And that's a nightmare for them. So how this will look like in the future, or what they imagine, is to have remote operation control centers with a couple of operators. And these operators then operate a whole fleet of drones. They're all automated, but obviously there might be alerts or there might be things coming up. And then an operator just gets pointed to that one drone. He needs to resolve it, and then he gets back to the full picture. And so they need to be really flexible in how these systems communicate. And so from our side, what we need to do is just to present an interface that they can work with. And then all this other stuff we don't have to deal with for the moment, because there's solutions going to be available soon. Yes, up there?
The basic rule to land an aeroplane or an helicopter is to face the wind. If you have, let's imagine, 100 kilometers of wind, and I see this huge facing surface, how is it manageable?
Yeah, so the question was about susceptibility to wind and gusts as well. So obviously that's a topic for any aircraft. As long as you face the wind with these, you can land at pretty much any wind, depending on how gusty it is, obviously. With Aero Mini, we sometimes, when the wind is a bit, like picks a bit up, we take off with 45 degrees wing tilt, and it just comes up straight. So you can compensate for the wind quite easily. Of course, there's a certain boundary to how much wind from the side and especially from the back you can tolerate. But they're surprisingly well behaved in wind. One of the constraints also is that if you have sideways wind, you compensate with roll, but then at some point your wing tip will kind of hit the ground, and at the latest then you need to start facing into the wind and bring your wing tilt forward. Yes? Yeah, question is about sustainability and how the numbers compare with a helicopter on Aero 3. I'm sure this question is asked. I don't really know the answer, to be honest. What I can tell you on Aero 2, we have about 4 liters on 100 kilometers. 4 liters of fuel for 100 kilometers. And if you compare that to a car, where there's also a lot of other losses in the tires and whatever, it's relatively attractive, especially as it's super fast and point-to-point. And compared to a helicopter, all I can say is just the aerodynamic concept is way more efficient, because you actually have a wing that flies, and also you fly a lot faster, so you even cover more distance. But the exact numbers, I don't know. And also, what we have to keep in mind, this is really just a stepping stone to make it fully electric at some point, or to have fuel cells or anything in there. Because we can accept, if you give me today a fancy box that makes 15 kilowatts, I'm more than happy to take it if it's not too heavy. Yes? Who will be operating the flight from A to B? Yes, so one of the things we had to agree on internally is whether to call it autonomous or automated, because it's definitely not autonomous. Autonomous, in our understanding, would mean it makes its own decisions based on a lot of inputs. So it flies automated, it gets a set of waypoints, and a really high-level logic abstraction of saying if you lose the link for more than a certain time, you start loitering, or you start going to your alternate waypoint or something like this. And we try to keep the operator as tight in the loop as possible. So there is an operator, but he's not actively steering anything. He's just pushing buttons on a really high level. So the abstraction level we imagine is more on the scale of proceed with the mission, wait, so loiter, or abort and fly back, something like this. And then, of course, you can start blaming the operator if there's issues, because otherwise you take, as a company, you take the full risk if there's accidents and stuff. Yes? BVLOS, beyond visual line of sight. We right now fly extended VLOS with the big ones, and we have trial setups on the small ones where we fly BVLOS. We had a test of our C2 link, command and control link, where we flew BVLOS, yes. And it performed surprisingly well. So the question is always, how does the link stay online for the whole range? There's a lot being done with 4G and 5G cellular technology, also SATCOM, to really fill in when there's no cellular at all. There's other approaches, especially in the US, where they have ground-based infrastructure. We try to stay away from it at the moment, just to be able to fly everywhere. But there's nice projects also with setting up ground-based infrastructure to have really good link quality, especially as there might be just routes where these things fly, at least in the beginning. Yes? Parachute rescue systems. This was, even for this one, for the small one, this was a discussion. The thing is, do you actually add safety with a parachute or not? Because if you pull the parachute, it just comes down uncontrolled. And so we follow more the philosophy of having it over-actuated and redundant. Even our flight controls, they're all redundant, and you can basically have any single system be killed, and it should be able, or it will be able, to come down, maybe with some degraded performance, but should be able to come down in a somewhat controlled way. And if you would fly over a city and you pull the parachute, this can still hurt someone with the 200 kilos. So we decided against using parachutes. Yes, up there? So on Aero 3, we don't yet have a prototype working, so I can't tell you for sure. On Aero 2, we target the hover time. So hover is about 4 to 5 times more expensive than cruise. And so our batteries, they just have to be big enough to feature about 3 standard procedures, so 1 takeoff and 2 go-arounds. And that translates to about 3 minutes of hover. And if you compare that with pure electric approaches, this is really a small battery, but it's basically all you need, because as soon as you're wingborne, your generator kicks in. Yes?
For the autopilot, do you use an off-the-shelf solution, for example, a Banshee, or do you do that yourself?
Interesting question. It's what kept me busy the whole year. No, we do it ourselves.
Regarding IO3, it will be with passengers. The question, have you already been in contact with EASA or FAA to define the certification requirements? Because it's between aircraft and helicopters, so it's not Part 23 or Part 27.
Yeah, it's a challenge, because the regulations are only about to get more clear. On Aero 2, we follow Part 23 as a reference, but then we can make big use out of the fact that we fly over sparsely populated area and basically don't put anyone at risk. And that's a huge gain, because you can exclude most of your catastrophic failure cases. That means all we really have to prove on the drones is that we don't breach the operational volume, and we then just contain the operational volume in a way where we don't fly over populated areas, basically. For Aero 3, I must say I'm not really aware of what exactly the plan is there, but we work with some good people from EASA on exactly these questions, and we have people experienced with these kind of things. So our head of design, he was building and certifying a flying car in Slovakia, which is, I think, was a two-person thing. But so yeah, I think they followed also largely Part 23.
Another question regarding the materials. You probably use a lot of composite, right? And did you already plan also the, let's say, resources and let's say, money and budget for certifying composite structure for with passengers? It can be quite heavy.
Yes, so the question is about composite and certification. Again, as Aero 3 is more down the line, I'm not the expert on it. We have our people on the stress analysis side. They worked in Boeing before, and they started working with composites. So from my limited understanding, I'm more the systems guy, but my limited understanding, the whole story is that with composites you have multi-load path, and you can accept certain degradation in your fibers, and you don't have crack propagation. Whereas in aluminium, or whatever else you use, you need to inspect it on a regular basis, and once you have a crack, the crack might grow, and in a composite it's constrained. So what I understood is that it's more straightforward to go through certification of composite, but I'm not the expert. Yeah, that's...
You don't do it by analysis, but by test. That's why I ask about the budget resources. Often it's a point that is neglected in this type of projects.
So the good thing is in Aero 2, which we are building now and bringing to market, we don't have to exhaustively test it at all, because we can much more follow the way you would do it in automotive industry. So you basically have to prove your production, and just by statistics, you have to prove that the quality is sufficient, because you don't endanger people fundamentally. And all of this will teach us how to go to Aero 3, and that's one of the reasons why we start small. Otherwise, there's so many fallacies you can get into. Really good point. Yes?
I was wondering, the Aero 2, what kind of video transmission system are you using? Like something from the FPV industry or something else?
Yes. So currently we use, or we have the requirement to have real-time or low latency video link, of course. And so one system uses the DJI, obviously, because it works super well. I'm also, I also got to know it because of FPV flying, and it's super smooth. And as a backup, we use HearLink, which is a bit higher latency, but still as a backup, it's good enough. And as we have quite a good level of stabilization on the aircraft, we can even accept quite a bit of delay, worst case. Yes? It's an interesting question. So it's about actuation of the wing versus flaps, and actually also versus pitch. Because if you, like our longitudinal dynamics, which, for example, wind gusts or in general wind compensation, you have these three methods to cope with it. First of all, and the fastest of them is collective flaps, which you can use on the short horizon. Then medium horizon is your pitch attitude. And then kind of the low pass integrator behavior is adapting the wing. And so the wing is not super fast. It's also highly geared and not backdrivable. So in case the motor or something fails, it would just stay where it is. But that makes it, in order also to not make it super heavy, it makes it relatively slow to move. But as we can compensate with the collective flaps and the pitch, it's perfectly fine. But standard transition takes about 10 seconds. So that's roughly the speed of the wing tilt mechanism.
I think we slowly come to an end. If there are any other questions, I think you will stay here a little bit longer.
Sure, yeah.
Then we would like to thank you a lot for coming here. Julien will present you with a little gift.
Wow.
Some praline for later, and also if you want to share with the team, I mean that's your responsibility if you want to.
I'll see. Thanks a lot.
Thank you very much.
It was a pleasure.
Timon,
Thank you very much.
for this nice explanation.
And yeah, as I mentioned, we will have a little apero. I have to disappoint you. The one just in front is not from us. That's the one from ETH. But we have ours just across the wall, so we have to walk left, and then just as I mentioned, across the wall, there's a foyer where we have our little mini apero. We would be very happy if you stay for a conversation. If you have questions about Dufour, he will be there. If you have questions about the Academic Aviation Association, we will be here. And thank you all very much for coming. And maybe see you next time.
Thanks a lot.